All right, so I have a timer set for 5 minutes. During this 5 minutes, I want you guys to do potassium. I want you to do each of the 3 representations for potassium. Then at the end of this 5 minutes, I'll show you the correct answers. All right, 5 minutes. Have at it. If there aren't any more electrons to make it S2, right? If that's the highest occupied orbital, perfect. I guess perfect is pretty uncommon. That's clearly there. How many electrons are in here? 1, 2, 3, 4, 5, 6. Is that what is room for my 3p6? So everything 3p and before is represented by that. All you have to write after. No, wait. Mr. Johnson. Oh, there's 3s. Yes. 3s. I don't know if this is right. You told me yesterday that 4s comes before the 3p. That's true. That's correct. You are correct. About 2.5 more minutes. Try to get all the way to the orbital notation so we can check that off.
Noble gas configuration.
Guys up front, we're going to go over this. Make sure that we got the correct answer going. Potassium, electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, when I go backwards from potassium, the first noble gas that I find is argon. And argon brings me all the way up to this 3p6. So argon is actually going to replace all of this. So all I have to do is write argon and then 4s1. Orbital notation is going to be kind of annoying, though, because I got to squeeze all of this stuff into this small space, which I'm not going to grade you down if you spill out of the table here. 3s. Oh, that's S. 3p. 1, 2, 3 suborbitals. And then 4s. Now let's throw in them arrows. Arrowed. Bam. And that, ladies and gentlemen, is potassium. Represented very well. All right. We are going to spend 7 minutes, and I want you guys to do numbers 3 and 4. That's calcium and cobalt. Now that we've done a couple, hopefully this goes quicker, so I'm going to give you less time. But you're going to go over numbers 3 and 4. That's calcium and cobalt. At the end of this 7 minutes, I'll go over the answers. 7 minutes. Have at it. You're still being asked to do the same 3 representations. You're just looking at calcium now and cobalt. After 4s, would it be 3D? After 4s, you fill the 3D. Yes, that's correct. Why is it like that? Because experimentally, we see that 3D, the 3D orbital, is higher energy than 4s. Yes, the D orbital has 5 suborbitals, so it's going to have 5 little lines. All right, let me get your attention while you guys are doing this just for a moment. A few of you guys you've realized, and correctly so, that on some of the notations in the notes and in the book, some of them tend to be backwards. Like in the notes, it wants to list 3D before 4s, even though you fill 4s first. The reason that is because there's this general convention where people want to list that principal quantum number, the 3 in 3D. They want to list that with the other 3s, like the 3s, the 3p, and then 3D. Then they want to go to 4s just to keep all the 3s together, all the 4s together, all the 5s together. That's just a convention that they like to do. That does not mean you fill the 3D before the 4s. I personally don't appreciate that particular convention because it's confusing to you guys. So remember, you do fill the 4s before the 3D. You do fill the 4s before the 3D. The notes are correct. It's just that I don't actually care for that particular convention. I wish it was a little bit different, but it's not, and we got to deal with it.
So does that mean for a D, for the any letter D, the subscript could reach up to 10?
Yes. Once it gets to 10, it's full. If it's anything below 10, it's not full. That means there's some number of unpaired electrons.
So we follow the notes when we
We do 4P and
When they write it out.
4P goes up to 3, right?
I don't know how you use it.
This doesn't mean, they decided that this doesn't mean this is the order in which they fit. That's what they decided. We're just going to have all the threes in order of four. And so what you can do is, as I do, is write it out in order of how they actually built. And then I'll have to go back. But see how 4 is actually lower than 3D? That means you build it. That's what this is trying to show you.
He said with the
That
3D before S, I don't think it really matters how you write it. As long as, yeah, it's the same thing no matter what. It's not like you're multiplying to a certain direction. Whatever. You still
my dad ended up putting safety.
two is from P2. P4 with P4.
No, this is still
Yeah,
4x. Also, where calcium doesn't have calcium doesn't have You will have to worry about it.
Because like, it seems like it's this, but for S2, I literally just like go in order. So it's 1S.
It's just one of those, like, you just memorize. There is no one P. The first P is 2. Right? So we get to this. We start with 2 P. There is no 1 or 2 D. The first D that happens is 3. So we just have to remember when we get the first D, it's 3.
So this would be 4 or 5.
Yes. 3D, 4D, 5D. And S, when we get to F, the last academic series, that's F. But the first F we ever get is 4. So when we get to here, we're going to go 6S, 4F, 5D. That's the part that we just memorize. So we bring back all the numbers. Okay, about 90 more seconds, and we'll go over these answers.
No, like to the church classes. The catechism with Mary. She shows us the pages.
So you got enough?
What's sulfur like? What's the Johnson, you're making us do this, and the book has it written out already.
Yeah. I don't want you to copy the answers. I want you to do it. That's why I said don't use your book. Use your periodic table.
Do we have to do all of the orbital diagrams? Because I know they get really big.
Yeah.
Right now, yes. Now, realize I'm wanting you to do the really long ones right now just so you're for sure good at them. Later, I'm not going to ask you to do the big long one. You're just going to use noble gas notation. But we have to make sure we know what noble gas notation stands for before we do that. But realize I'm only making you do one really long one. I mean, cobalt is like meh, meh. Hold on, Johnny. We're going to go over these answers right now. All right, guys, let's look at some answers. First thing we're going to go over is calcium here. Find calcium right here. It's number, let me move the timer out of the way. So if we look at calcium, we find it's number 20, so I have to account for 20 electrons. And when I go to do cobalt, I'm going to see it's number 27. So I'm going to have to account for 27 electrons over here. Hooray! This is going to be a blast, trust me. So calcium, 20 electrons. Let's go. 1s2, 2s2, 2p6, 3s2, 3p6. Now let's see how many electrons I have so far. 2, let's do this, 4, 6 is 10, that's 12, that's 18. I need to count for 2 more. So after the 3p, I'm going to go to the 4s2. Now I have 20 electrons accounted for. Noble gas notation. I'll find my calcium, go backwards to the nearest noble gas, which is going to be argon. Argon, and that accounts for all of this, everything before that. So all I have to write now is 4s2. Boom. All right, now I got to do a lot of line drawing. The 3s, there's a 3p, and then a 4s. One line there, 3 here, 1 there, 3 here, and 1 there. All right, here we go. Lots of arrows. Oop, got my down spins. And that is calcium. Go cobalt. I'm accounting for 27 electrons here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7 is the last orbital that I'm actually going to fill. Now, like we were saying before, if I'm going to submit this as my final answer, after I've established that 3d7 is going to be my highest, 3d is going to be my highest occupied orbital, I'm actually going to take this and I'm going to slap it actually in between the 3p and the 4s, just so all the 3's are together. And that's really the only reason. This, writing it like this doesn't actually tell you the order in which they fill. Technically speaking, they just want all the 3's to be together and all the 4's to be together. Julia?
Does that mean that after 3D would come 40?
Not 40, it'd be 4p.
4P, yes.
4p would be after 3d. 4p, no, then 5s. Then 4d, then back to 5p. Tiffany?
So for the noble gas configuration, we put in the brackets the element, and then we put 3d7 for S2, or we put the 4s2.
You would go, that's a good question. Start with the smaller number first. That's actually how they want you to record this. They want you to go argon 3d7 4s2. That's actually how they want you to write your final answer, even though that isn't the order in which the orbitals fill. They just want your principal quantum numbers in order from smallest to largest. So personally, right now, just because we're learning the process, I'm actually okay with either one. As long as it's 3d7 and 4s2, right? If you start saying things like 3d2, 4s7, then I'm like, haha, no. All right, let's write this orbital diagram because it's nice and long. I'm going to start writing really small. 1s, 2s, 2p, 3s, 3p, 4s, and 3d. Now let's fill these arrows. Four, 5, 6, 7. Boom. All right. The next question I want to look at is number 9 down here. So eyes up front, guys. Eyes up front. The number 9, explain the conditions under which the following orbital notation for helium would be possible. This should sound pretty familiar. You know why? This is one of the questions on your secondary worksheet. Okay, a lot of people were confused by this, so I wanted to go over this specifically right now. If we remember, earlier in chapter 4, we had these energy diagrams that look something like this. This is the ground state, and then we had these different energy levels. Okay, and we would have a certain number of electrons in this ground state, and if we absorbed a certain amount of energy, right, in the form of a photon, if that photon was of sufficient energy, one of these electrons could jump up, and it would now inhabit this higher energy level. What if I were to tell you that this ground state was actually 1s, and this next energy level was 2s? So in order to get one of these electrons out of the 1s and up into the 2s, like we have here, what it requires is the absorption of a photon. So explain the conditions under which the following orbital notation for helium would be possible. All we need to have happen is that the atom must absorb a photon to excite an electron into the 2s orbital. That's all it is. This is the excited state of helium. This is an excited helium atom. It's as simple as that. And we're actually talking about stuff from previous sections. Now I want to look at number 2, and I want you guys to answer this, and I want you guys to shout out the answer when you get it. A little bit of a race here. Number 10, which of the following electron configurations is impossible for an atom, regardless of whether it is in the ground state or an excited state? So in number 9, we looked at this kind of weird situation. We said, oh, if it's in an excited state, that's fine. But there's one of these that even if you take into account like the possibility of an excited state, one of these is not possible. You guys try to figure that out now. I'm hearing D. I'm hearing B. Tyler, why do you think it's B? Ah, 1s3. Right? Because this 1s orbital, any s orbital, can hold a maximum of 2 electrons. If there's a third electron to be housed, it must occupy a different orbital because there isn't enough room in the s orbital to house 3 electrons. Good eyeballs. All right, let's flip this over to the back. There's a back? It will be. All right, guys. We're going to do number 12 here. Given the electron configuration for oxygen being 1s2, 2s2, 2p4, answer the following questions. First, how many electrons are in each of these oxygen atoms? How many electrons are in these oxygen atoms? How do you know 8? Well, it's on the periodic table. That's true. But it's also right here. 2 plus 2 plus 4 equals 8. You did say that. Good on you. Yeah. Ocho. B, what is the atomic number of this element? 8. Because right now we're assuming that these are electrically balanced atoms. And if you have 8 electrons, you have 8 protons, making the atomic number 8. C, write the the orbital notation for oxygen's electron configuration. We got 1s, I got 2s, I got 2p. Yeah, orbital notation, not the electron configuration. So I got to count for 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Boom. Nailed it. So now let me ask you this question, guys. How many unpaired electrons does oxygen have? How many unpaired? 2 unpairs. You see these bad boys? They have no friends. They're like the Johnny Bennett of electrons. Okay? E, what is the highest occupied energy level? Well, it says energy level, so just 2. Okay, if I asked highest energy orbital, you'd say 2p. But since this is just a main energy level, that's the entire period, the entire row. So it's 2. Yes.
But you couldn't fill one up while the other one be filled.
What was that question?
I thought you couldn't fill one up while the other one be filled. Like, doesn't that one need another, like, opposite spin?
Are you talking about these 2? Well, there's nothing else to put in there. I only have 8 electrons to start with. Right, so I have 1, 2, 3, 4, 5, 6, 7, 8. That's all 8. If there were 9 electrons, yeah, I'd pair this up. And if there were 10 electrons, I'd pair both of these up.
Why don't you just put it 2p, like, with only 2? Instead of, like,
Because the 2p has 3 suborbitals. And so remember, Hund's rule says you have to fill each suborbital singly before you get to double them up. So you got to spread them all out. So this electron right here was the last one that I put in. This downspin one right here, that was the last one that I put in. I put in these 3 ups first. All right, how many inner shell electrons does the atom contain? Inner shell. Nope. Inner shell. 2. It has 2 because the 2s and the 2p are both in the second row. That's the highest energy level. So 2s and 2p are both the highest energy level. The inner shell electrons are anything underneath that. So the only things we have underneath that is the 1s. So we only have 2 in there. All right, and in which orbitals are these inner shell electrons located? The 1s.